Okay, let's go on to our next topic and talk a little bit about how resistivity affects temperature. In a conductor, when the temperature increases, the particles will move around faster. This is true in any solid. The particles are going to move around faster, exhibiting these larger thermal motions. And that's going to mean that the number of collisions will increase. So as these particles are bouncing around in this very high speed thermal motion, they're going to bang into more things, and that's going to impede their motion further. So the resistivity of the material will increase with temperature. And the way we write that is actually very similar to how we write the increase in length that we see with thermal expansion. You should recognize that the formulation looks very, very similar. The resistivity at some temperature T is equal to a reference resistivity multiplied by this factor, 1 plus a conductivity, sorry, a resistivity coefficient alpha multiplied by the difference in temperature between our temperature and the reference temperature. And so we may just simply write it this way, but that delta T is just T minus the reference temperature, where rho naught is a resistivity at that T naught. So here's a table of a few resistivities and thermal coefficients to give you a feel for what this looks like. Again, remember, these are conductors with resistivities typically on the order of 10 to the negative eighth, although some conductors, tungsten, nichrome, and carbon, may have much higher resistivities. And thermal coefficients tend to be on the order somewhere between 10 to the negative fourth up to 10 to the negative third for the most part. Carbon does some weird things. That is actually a negative coefficient. The hotter carbon gets better of a conductor it actually is. That's because it's a semiconductor, really, and it acts a little bit strangely. So let's take a case here where we have a 1 meter long copper wire with a radius of a half a millimeter at 20 degrees Celsius. And we want to know what's the resistance at 20 degrees Celsius, what's the resistance at 200 degrees Celsius. All right, you can go and you can calculate the actual resistance of that wire with those dimensions on your own. We've done that before. That part is old news at this point. I want to look and see what happens to the resistance when we change temperature. And the main reason I want to do this is because there are actually two things going on. The resistivity is going to increase as temperature increases, but the physical dimensions of the system are going to change as well. The wire is going to expand as it heats up. Its length is going to become greater. Its cross-sectional area is going to become greater. So what happens? How do these two factors play off one another? So the first thing, let's look at the temperature variation in resistivity. So I've written out our resistivity temperature equation. So here I calculate at 20 degrees Celsius, and unsurprisingly, because rho naught is the resistivity at 20 degrees Celsius, our delta T is just equal to 0. Temperature minus a reference temperature is 0. And so our resistivity is just our rho naught. But when we crank the temperature up, we find that everything is the same except that our temperature jumps up to 473. So this thing comes to be about 180 Kelvin. And if we just evaluate this expression in the parentheses here, let's leave this as rho naught. If we evaluate this expression in the parentheses, we come with 1.71. So basically, the resistivity, the hot resistivity, is 1.71 times the cold resistivity. It's 71% greater. The resistivity has changed a lot. It changed by 71% over the cold temperature. That's a big difference. So what happens to how does the physical dimension of the system change? All right, remember that our resistance equation looks like rho L over A. So it's really this L over A term, the length divided by the cross-sectional area, that we want to know. We want to know what happens there. All right, so go back to thermal expansion from first term, and you have this expression, right? This is what I said. This thing looks, the resistivity expansion looks, or resistivity increase looks just like thermal expansion, just with different quantities. Here I'm writing the thermal expansion coefficient alpha as alpha sub L to say that this is a linear expansion coefficient. It's not the same value as that's not the same alpha as the resistivity alpha. The resistivity alpha, remember, is on the order of 0.003 per Kelvin. The thermal expansion coefficient for copper is small, 17 times 10 to the negative 6. So when I plug that in there, again, I'm going to evaluate just this expression. I'm going to get about 1.003. So that means that the length changes by about 0.3%. The length increases by about 0.3%, a small amount. What happens to the area? We have a similar expression for area, where we can write the area at some temperature T expands by this much, where that gamma can be written as twice the linear coefficient, again from last term. And I use that because we have that linear coefficient on hand. We multiply that linear coefficient of 17 times 10 to the negative 6 per Kelvin by 2, we get 34 times 10 to the negative 6 per Kelvin, and so we come up with this factor. The area increases by about 0.6%. So when I put those two things together, our L over A looks like 1.0306 L naught over 1.0612 A naught, and we get this. The physical size term is only about 0.3% smaller than the original physical size term. All right, so when we put these two things together, what do we get? The resistivity is increased by 70%, while this physical size term has decreased by 0.3%. Clearly, the resistivity term dominates. It's immense in comparison to the physical size term. Why is that? Well, it's that the resistivity changes a lot more. In order for the length to change, we've got to stretch all these bonds to make the solid bigger. But in order for the resistivity to change, all we need to do is make that particle move a little bit faster, and it's going to be banging into a lot more things. And that's reflected when we look at these temperature coefficients. The resistivity coefficient is about 4 times 10 to the negative third. The linear expansion coefficient is about 2 times 10 to the negative fifth. That's 2 orders of magnitude. The resistivity for copper changes about 100 times faster, 2 orders of magnitude faster than the length will change. So in general, for most materials, this is true for most materials, not all of them. Some materials have very large thermal expansion coefficients or very small resistivity coefficients. But for most materials, it turns out we can ignore the thermal expansion and just treat it as a resistivity expansion. When we do that, we can, instead of writing that resistivity as a function of temperature, we can write the resistance as a function of temperature. Now, this is not precise because the length and the area do change a little bit, but it's pretty close. It gives us a good idea of what the resistance looks like. And essentially, every resistance thermometer works off this principle by measuring the change in resistance with temperature. Okay, so let's put this into use. I'm going to take a light bulb with a tungsten filament. It has a resistance of 15 ohms at the reference temperature, at a cold temperature of 20 degrees Celsius. And it has a resistance of 160 ohms when it's hot. And so what I want to know is, what's the hot temperature of the bulb? And then I want to talk a little bit about how the current changes with temperature. Okay, so let's pull out that resistance equation that we noted over here at the bottom of this page. And we're going to write it for the high temperature, our reference temperature, the cold temperature, and our resistivity coefficient alpha. So let's do some manipulation. Divide both sides by RC. Let's swap the sides. Let's divide both sides by alpha and add the TC to both sides. We get this expression. And now we can just plug things in. So our cold temperature is 293 Kelvin. Our alpha is 0.060 per Kelvin. And remember, that's alpha to the negative 1, so it's 1 over alpha. Our hot resistance is 160 ohms. Our cold resistance is 15 ohms. We'll subtract the 1 off there. We're going to come up with a number that looks like about 1904 Kelvin. Call it 1700, a little under 1700, 1680 or so degrees Celsius. So it's a nice hot filament. Now, what happens as the filament heats up? The resistance increases, but Ohm's law will tell us what happens. The potential difference is going to stay the same. That's being maintained by an outside source. So delta V stays the same, but the resistance increases, so current must drop. It draws more current to start with when you first flip on the bulb, and then that decreases until it has reached its operating temperature, and then it stays steady. Now, what happens to power dissipation? So we can use these three expressions here, but we don't want to use this one because we know that the resistance increases and the current decreases. Which one of these happens faster? What happens to the power dissipation? It's hard to tell. But we can use one of these other two because potential stays the same and resistance increases, so the power dissipation decreases. It uses less power as you go on. It uses a lot of power initially and then less power, and then it maintains that steady point. If I look at this expression, again, delta V stays the same, but the current decreases, we just saw. So the power output decreases, says the same thing. So more power is dissipated initially. Where does that extra energy go? Once the light bulb is on and operating, all of that energy is going to be dissipated in terms of visible light and infrared light. This is actually the radiation that we see when we talk about transfer of thermal energy from one place to another in the form of radiation, of infrared light, of visible light. That's this. We'll talk more about this a little bit later. When you say that incandescent light bulb is getting hot, when you put your hands near that incandescent light bulb, you'll feel that warmth. That is primarily infrared light that your skin is absorbing. But why do we have such a high power initially? Well, the reason is we need to heat up the bulb. Initially, the resistance is lower and the current is higher. We have this large power output, and most of that power is going into heating up the filament itself. Once the filament gets hot, current drops. We have a smaller power dissipation. Now, interestingly enough, a funny thing happens over the lifetime of a light bulb, of an incandescent bulb. That incandescent bulb will slowly boil away the filament. Basically, little bits of that filament will evaporate away. What happens to the filament? Well, the filament doesn't change much in length, but the cross-sectional area decreases. What does that do to the resistance? As the area gets smaller, the resistance will increase, which means that the current flow will become less. And it also will mean the power dissipation is less. And what that will end up meaning is that an incandescent bulb will get dimmer as time goes on because the current flow through that filament will become less and less due to the decreased cross-sectional area. And that is our discussion on temperature change and resistivity and resistance change.